Hello friends, this is a video for an introduction to an article I have published on the web. Now I am an independent non-academic researcher and this article is a research paper connected with calculating the value of pi. There are many reasons why I am publishing this article independently, and one of them is that the information is very simple and obvious. Now taking it and writing it for a science journal, I'm not sure how much of value it would be, and it would take time. So because I need to share this information as quickly as possible so you can use it, I'm sharing this as a web page. If I need to publish it in a science journal, I can do that process separately if necessary. But I want to let you know that the information that is contained in this article, I was not able to find it on the web anywhere. So I think this publication on the web would help you if you have not come across it. Now, what is there in this article? So I have found out a way of improving the Madhava Gregory Leibniz series, the convergence of the Madhava Gregory Leibniz series. This series is actually a very old method for calculating pi. So the calculation of pi, there are a lot of formulas, and this formula is like the holy grail. It's a very basic formula. It's rooted in very strong trigonometrical derivation process, and the only problem is that the series converges very slowly, and they have said that it is not very very useful for practical applications. Now they use a value where x equals 1, and that is what we call as the Leibniz formula for pi, or pi by 4. Now, for over 27 years now, I have been spending time investigating like a bunch of systems and related philosophies in my own ad hoc manner. Now, among many of the systems that I studied, there is one for which I need to build an experimental mathematical system. Now, I'm not a mathematician myself, and I needed some kind of proof that was embedded in nature that would connect all these mathematical equations that are in the experimental system. Over the years, I found an axiomatic approach, but I was not satisfied. So finally, I got an approach for a geometry based proof, and I proceeded to create a mathematical system around it. But I needed to prove the relationships, and there were multiple paths that I could take. So I turned to trigonometry. And I decided that if I could get one universal constant or a bunch of universal constants, like for example pi or Euler or the golden ratio, if I could derive and connect that and show that, oh, I'm able to arrive at the value of pi, then the mathematical system, experimental system, would be stable. Now during this process, I came across an anomaly when I was trying to calculate pi. Plus at the same time, I found out that whatever way I approach pi, it generates the Madhava Gregory Leibniz series at the end. Everything cancels out and the arctan of x shows up. The anomaly is still there. There's a problem that I have not sorted out. But I tried to search this information on the internet and see what is there with this series that I can actually use. And they say the series converges very slowly, but what I saw was otherwise. I searched to find the derivative proofs and any other methods that were there, but everything that they tried to do with the series is they tried to put extra values in it and tinker it and try to change the constant and balance it out. You don't need to do anything with the series. The series itself is very pure. It directly gets you the value of formula. What you need to do is find the value of t where you can actually make, you can put that value of t and you can get the value of pi. Now there may be a reason behind why mathematicians have ignored this, but like I said, the series looks quite stable. So what I've done is I have put all this information that I worked on the series. I've shown how to improve the conversion of the convergence of the series, and when I experimented with the series, I found out that if you really make the convergence as steep as possible, you need only one iteration to get a decent value of pi. So when you look at it, all of a sudden the series goes out of the window and you're looking at something very basic, something very rudimentary, a rudimentary approach to calculate the value of pi. Now, this information is also shown in the paper, and this is written like a scientific paper, and I've released it under Creative Commons license, so there are no restrictions. You can print it out, you can use it and advance your research on pi if you have not come across these kind of equations. Now if you are a programmer, you can take this equation if you're interested and actually put various parameters, change various parameters and make it converge fast, find a better way to increase, there's a value called k and t that is called tan dip. You can see a way of increasing the calculation of tan dip and make it faster. Now if you want to comment on this, please use YouTube. But if you have some technical questions, I would suggest you use the Math Stack Exchange, because there are people, real mathematicians, who can actually address all technical queries. They are very sound. So, and there is you can also debate a lot of stuff over there. And if you put the, let us say, Madhava Gregory Leibniz pi, Madhava dash Gregory dash Leibniz dash pi, like a keyword in there, or MGL series as a keyword in there, then I will search it up. I can search it up and then can link all of these things and see if there are any things you want to mention for me. Now, this paper is not my exact research. This is not where I'm heading. But I will improve this web page over time, put information in it, more information, so it is complete. But then if there are other web pages that are just like this, because I didn't find any one of them right now, so I will see, I can link them to this web page as time goes. So please feel free, to share this video and build on it, and all the best on your contributions to mathematics. Thank you.